Hi everyone, we're back. We're going to skip this part right here for now because that's in a later chapter, and so we'll come back to that later. Let's finish off with the anhydrides and then we'll wrap up the chapter. So right here, this is about how to synthesize an acid anhydride. You guys know that on the top of the reactivity ladder that acid chlorides and acid anhydrides are the most reactive. So acid chlorides are very reactive, so if I just want to make this anhydride, then I just need to have this additional group on it right here. So how do I get that group? Well, I put it into the nucleophile. So here it is as a negative charged anion with sodium as the counter ion. Okay, so this part right here will attack the carbonyl group. So here I'll draw it right here. And let's say my acid chloride is here. Alright, so then it's pretty simple, just this as usual, and we get our tetrahedral intermediate. And then from here, we have this tetrahedral intermediate right here. And then you can see that I'm going to lose this group. Chloride is a good leaving group because it's a very weak base. All right, and HCl, its conjugate, is very strong. So that's how we get this acid anhydride. And acid anhydride or anhydrous means without water. And the term acid anhydride actually comes from two carboxylic acids coming together and losing water. So if you could picture, here's one and here's another. If these two got together and lost water and you tied them together, you would get an anhydride. So it's from acids losing water to become an anhydride. Okay, that's where the name comes from. Esters you can use, anhydrides, once you make them, can be used to make all kinds of other things. Any of the other groups on the ladder, like amides, esters, carboxylic acids, you should be able to make any of those from an anhydride. You just need to identify what is the nucleophile that you need. So if you look at these two, just see that, oh, this group is being replaced by this group, and so we need some kind of nucleophile that has that group on it. So I'll make it into, you can go one of two ways. You can either do sodium alkoxide, so sodium methoxide, ethoxide, whatever that R group is, or you can make this into an alcohol. And because this is so reactive, because this is such a good leaving group, this will react just fine. You don't have to have it already negatively charged. So either one of these is fine. I'll show you with the alcohol. Okay, so the mechanism would be, I've got this acid anhydride here, and then I have the alcohol that attacked. Of a carboxylate ion with an R group. That comes from this anhydride this is the leaving group of this anhydride. If you are using an ester, let's say you're interested in doing an ester synthesis, which anhydride would you rather start with? I think you guys know that if I had a nucleophile, so there's lots of choices for where this nucleophile attacks. So it could either attack here or it could attack here. So in this case it doesn't matter where, because either way you end up with a methyl group on there. So you have this acetyl group here and acetyl group there. So you're not going to get different products. But if you had a nucleophile with this other one that's asymmetric, you could end up with an attack there or an attack there and have two different outcomes, so two different esters. So in this case, you probably would want to stick to the one where you only have one possible ester, so you don't have a mixture, unless that's what you're going for. Draw both products from this reaction, so now you can see what happens if I have an amine, and I have this acid anhydride. So you probably see two different ways that this could attack. So if I do the attack this way, and they're not asking me for a mechanism, so I'm just going to sort of use a bunch of arrows just to figure it out in my mind. Then I would end up with this eventually. I'd have to deprotonate this last, hydrogen here, but I would have that. And then in a different color, if I attacked here instead, then I think you can see I would end up with this propanamide instead. Okay, so So it does matter, and so for that reason you'd want to try to use a symmetric anhydride if possible. Alright, so here are just a bunch of practice problems, just like we did with acid chlorides. Just take acid anhydrides and just react them all and see all the different possibilities you can get. Again, it looks like a bunch of different reactions, and they are, but they're very similar in the mechanism. The mechanism is always nucleophilic attack, and this is a very good leaving group, so you pretty much will get those products. Let's go ahead and give these a try, and we'll go over them in a few minutes. Okay, so for this one, I'm taking this nucleophile and I'm going to use it to attack. And luckily this is symmetric, so I only have one choice of product, which is going to be this one. Okay, and then this oxygen actually is from the phenol that attacked. And I'm going to deprotonate this H later with another phenol. And so I'll end up with this. And if you want to draw out the phenyl ring, that's also fine. You can do that. Okay, for this one I will do the same thing. I'll use this and I'll attack here, doesn't matter where, and when that comes down you'll release. Okay, so and then if you want to, you can show the byproduct, which is the rest of the anhydride. You know, it will be like that. This one will be deprotonated because we are in a basic solution. This is a base, so there really isn't going to be a way to deprotonate there. You'll use excess because you'll have one of these molecules grabbing the H off of another one. So you could technically deprotonate there, except this is stronger base than that one is. Here as well you would end up with this byproduct up here. I'll just put them in parentheses because usually that's not the part we're trying to synthesize. So you'd end up with this benzoate up there. Okay, let's keep going. Here we have the alcohol here, and the anhydride is the reactant on the arrow. Okay, so here we would go like that. Okay, so my product is going to be this OH with acetyl group, and then don't forget the R groups on there as well. So we have this, and then you have your leftover group, and I've lost my color coding, so let me fix that. Okay, and here it is with the color coding, and then the leftover part of the anhydride is going to be this part right here. Okay. And then the last one, again, excess of this amine, because you're going to need one to pull this H off of the other eventually. So I'll just do this. So again, I don't want you to do all those arrows at once when you do the mechanism, but just for figuring this out, it's okay. Alright, now that H will go away eventually. You can, if you're not sure of that, just do the mechanism and you'll see that you can get another one of these and pull that off eventually. Okay, because it'll be positively charged later. Alright, so once we have that, we're going to make a different kind of product, right? This is an amide. Okay, so just if you know the mechanism, you can always figure it out. Okay, so nitrogen's attacking the carbonyl right here. Alright, and I need to fix the color coding. There we go. Okay, these are pretty straightforward, very similar to our acid chloride starting material instead of acid anhydride. The only thing is you get the rest of the anhydride left over as a byproduct. Alright, let's try these now. Identify what reagents you need to make these transformations. Let's do one of these together. So I'm seeing that I have a carbon unit off of here, and I have this alcohol group. I know I can oxidize that to get more oxygens in there, right? So I'm going to maybe think about oxidizing this to a carboxylic acid. And then if there's a way I could switch out the OH group for the ethoxyl group, that would be great. So how would we do that? Step one, oxidizing this to carboxylic acid, I could just use my Jones reagent or KMNO4 or, sodium dichromate, any of those reagents. Two, I would want to, there's two ways to do it. One is you learned about esterification earlier in the chapter, H+ and ethanol. So that's fine. Or you could do this route going to the acid chloride like that, and then you could go to the ester that way. So you could just add a second step thionyl chloride, and then third step ethanol. And that means that'll be a much higher yield in terms of, you get more reaction being driven forward, but because this one here is more reversible. But the downside is you have an extra step though. Okay. All right, so go ahead and think about this one then. All right, guys, for this one, I think you can see that I could get oxidative cleavage since I only want one carbon here. So that means that I get a carboxylic acid with oxidative cleavage. So I can use, if I use ozone with zinc, I'll get an aldehyde. Then you can oxidize it, or you can cleave it with KMNO4 in heat. That's hot KMNO4. Okay, and you can get that to work and be in oxidizing conditions already. And we usually do acid workup with that to get this H on there. Okay, so that's the first and second step. And then to go here, you could do the same thing we did here. You could either convert to acid chloride and then use ethanol, or you can use ethanol in acid and hope for Le Chatelier to push the reaction forward. All right, now for these are all esters, and so just to review, this is more end of the chapter kind of practice. So we've taken acid chlorides, done a bunch of reactions. Just now we did acid anhydrides, did a bunch of reactions. Now let's just get used to, okay, how do esters react? So these are all esters. Go ahead and give these a try, and we'll check back in a few minutes. All right, for this first one, I just picture hydride as H-. Okay, technically it's aluminum hydride, but if you did that, you would end up with an aldehyde, but then it says excess, so of course we're going to do it again, and you're going to end up with an alcohol there. All right, so hopefully you can see that. Same thing like with carboxylic acids, excess LAH turns that into an alcohol as well. This next one is a Grignard reagent, so I'm just going to do my addition elimination. So that means I'm going to end up with an ethyl group here. And I regenerated the ketone, I don't get the alcohol. Okay, if you want to, you can write, the byproduct, okay? And then next one here, this is a cyclic ester called a lactone. And you don't have to memorize that, but sometimes you see that. So again, LAH, I'm going to react that. This is going to open up the ring, interestingly enough, like that. And if you get confused, just count around 1, 2, 3, 4, 5. I have 5 carbons, including the carbonyl. 1, 2, 3, 4, 5, and then I have got this O-. Okay, and then you have another equivalent of hydride, so that attacks again, and you're going to get an alcohol. 1, 2, 3, 4, 5, and the OH, and you're going to work that up with water and end up with this diol. And then just go back and make sure 1, 2, 3, 4, 5, 5 carbons only. 1, 2, 3, 4, 5, 5 carbons. Okay, doesn't hurt to count. And then this last one, H3O+ means acid and water. So I'm going to activate it, I'm going to have my water attack, and I'm going to eventually lose that ethoxide group, so as ethanol. So I'm going to end up with a carboxylic acid. You should know mechanisms for all of these. Actually, they would help you so much to figure out what the product's going to be. Even if you don't write out the mechanism, because that takes a lot of time, just thinking through what's the nucleophile, and just sort of like I'm doing, figuring out how you come up with the structure at the end. Okay, I think that's much better than just guessing and trying to, memorize your way through. All right, propose a mechanism for this transformation. You can see there's going to be a ring opening. 1, 2, 3 carbons, 1, 2, 3 carbons. So that's fine. It's nothing crazy going on. So again, H3O plus is H plus in water. Okay, why don't I give you a minute to see if you can figure this out. I really need you to try, to work these out, because if you just follow along and you just copy what I do, that's not going to help you on the test. So my recommendation is think about the patterns we've learned before on what does acid do with the carbonyl group, how might there be ways of opening this ring up, where would it open up, and see if you can come up with this structure. All right, everyone, so on this one, what I would recommend is that you protonate this, because water is a weak nucleophile. It can't just come in. And obviously we need a water coming in because we have 3 oxygens and not just 2. So after we activate it, then water can come in. All right, so after I have that, then I'm going to be able to attack water. So I've got that right here. And water needs to be deprotonated. So eventually, I think you guys can see very similar to those reactions with the hemiacetals and the acetals and the, all those reactions we did. We want to have an elimination occur such that this group comes off. So we need this to be a better leaving group. So probably want to protonate this part, and I probably want to deprotonate this part so I can hold on to it. Okay, so there's my series of proton transfers. Once I do that, I'll end up with a protonation here and deprotonation here, and then I'll be all ready to do the elimination and break this bond open. So it doesn't matter which oxygen you use here, so you can use that one or you can use the blue one, and you can do that. And when you do that, we'll have one more step, which is to deprotonate this hydrogen right here. Okay, so to deprotonate this guy, I can use another water molecule and just grab that with my lone pair. And there we go. So hopefully you see that this looks really crazy, but it's not. It's just like all those reactions we've been doing already. Let's see what happens with amides. Okay, and here's an acid chloride snuck in here. All right, so amides with LAH. Remember, usually LAH takes down a carbonyl to an alcohol, but in this case, excess LAH actually takes it all the way down to the amine. All right, so that might be something that you just want to remember, because the mechanism for this is pretty long and detailed, but yeah, just remember it takes down this carbonyl group. Okay, this one here should be pretty straightforward. So this is an additional elimination. The acid chlorides are very reactive, so it has no problem making this amide. Excess means that you need something to take off the extra H later to neutralize this, because if I had an H here, it would be positive. So that's what the second equivalent of this does, is it provides that. And my last one here is hydrolysis with heat and acid. So I could picture this getting protonated. I could picture the water coming in. And I'm basically going to replace NH2 with an OH group. You should know the mechanism for that. Okay, so if you're not sure what it is, try writing it out. But you'll end up with mainly carboxylic acid. Okay, the reagents you need to do this transformation, I think you could see how you can piece together what we've done up here. So we went from here to an amide, and then we could go from an amide to an amine. So it's basically A and B up here. So what reagents do we need? First, our thinking is to make this into an amide. So we need to think about what we need to make this amide, which is NH3. All right, and then to go from here to here, it's a reduction, so LAH excess. And then to make sure that there's H's here, we often put water workup as our last step. All right, next one is propose a mechanism for these transformations. So you'll see this is very similar to what we did up here. Okay, so I'm going to skip these for now. Propose a mechanism. Oh, and one more thing. This one's acid catalyzed opening. This one's base catalyzed. So be careful when you do these mechanisms that when you have acid catalyzed, your first step is usually that. When you have base catalyzed, though, usually you can just go right in and attack. Okay, so that's going to be the main difference in these mechanisms. Make sure you don't have things that are super protonated. When you're in basic condition, there's not a lot of protons floating around. And same here, you don't want to have any OH minuses around if you're in an acidic condition. Okay, it just doesn't make sense. Okay, and the last one here, this is a pretty complicated one. So if you can, work on it, but there's plenty of other things to work on also. But it is something we went over, and it's the idea of it is that this is like a carbonyl group, this cyanide group. Okay, so if you treat this like a C double bond O, then you know that the O would get protonated. So same thing here. This sort of gets protonated here. And then you work through it where the water attacks and attacks right here. And then you end up with the nitrogen grabbing more hydrogens from the acid source, from the solution. Okay, so see if you can do that. And then just as an extra, exercise for your mind, think of all the reactions this can do next. This could become, we learned how to reduce it, right? This could become that, for example. Or you could hydrolyze this to a carboxylic acid. Maybe you could turn that into a C double bond OOH. Okay, so think about, and then from here, what can all this do? That can make an acid chloride, that can make a ester. There's a lot of things you can do from there also. All right, so I encourage you to look through that one, but this is a mechanism we did go over before. All right, and I'll do a separate video on the very last part.